Okay, let's start. So, hi, good morning, everyone. Thank you all for coming. So today we have our dear Izaskun Jimenez. She is astrophysicist, and she works with the massive star formation and, of course, also prebiotic chemistry in the interstellar medium. And she worked at a lot of renowned institutions, such as the Harvard Smithsonian Center for Astrophysics, the European Southern Observatory, the University College in London, the Queen Mary University, and the University of Leeds. And now she's working here as a staff researcher at CAP, and recently was awarded an ERC Consolidator Grant, which is amazing. And she's going to talk to us about that project. So thank you so much, everyone.
Thank you, Rita, for the nice introduction. Well, thank you very much for coming today. As Rita said, so what I'm going to be talking about today is about the research that we've been doing here at CAP in the past 6 years, which is actually the foundation of the ERC Consolidator Grant project. So I hope you like it. And before I move on, so what I would like to do is to thank all my collaborators, so the people in our group, and especially the young people who are the ones really pushing forward this project. Our collaborators here at CAP, Carlos Briones and Jacobo Aguirre. Jacobo is sitting there. And then also our external collaborators. And as you can see, so we have not only astronomers, but also people who are experts in millimeter molecular spectroscopy, who are actually the ones providing the key inputs to search for the prebiotic molecules that I'm going to be showing today in this talk. I would like to thank our collaborators who are experts in materials physics and also theoretical chemists, because they are the ones trying to understand the chemistry of these new molecules that we are detecting in the interstellar medium. So as you can see, so I'm an astrochemist as background, and as you can see, astrochemistry is a really interdisciplinary field because it requires the expertise from many different fields in order to move forward. So what I would like to show you today, so the main topic of this project is basically to try to understand the emergence of chemical complexity in space and to try to investigate what prebiotic species, which are the ones that we believe were involved in the origin of life, could form already in interstellar space. But if we really want to target all those key prebiotic species, the very first thing that we need to do is to look at what life is. And according to NASA's definition, so life is a self-sustaining chemical system capable of Darwinian evolution. So all the astrobiologists who are here probably know this very well, but I'm just showing this for the sake of the young people. So as you can see, so this sentence is a very simple, short sentence, but it really contains the three main properties of life. So life should be a chemical system, so that means that need to show a compartment, so it should be compartmentalized. It should be self-sustaining, so that means that it should be able to carry out the basic metabolic processes, and also it should be able to evolve in a Darwinian way. So that means that it should be able to storage and transfer genetic information, and therefore it should be able to replicate. So at the beginning of astrobiology, and especially in the field of origins of life, different groups were focusing on one of these three properties. So some groups were stating that compartments came first, or that metabolism came first, or that replication came first. However, in the past 10 years, there's an emerging theory for the origin of life, which is called prebiotic systems chemistry, that states that primitive Earth was a huge chemical reactor in which a wide or a high diversity of precursor components was available, and that all these precursor components turned in a progressive and in a concurrent way into the first metabolic self-replicating and membrane-bounded subsystems. So the type of molecules that we're interested in this kind of diagram, I think this is extracted also from Ruiz Mirazo, I believe. So in this scheme or this sketch that is plotted here, so the kind of compounds that we are interested in are these ones, the ones that we can find at the beginning of this process and that really provided the first steps into the formation of the first biochemical compounds. So our work hypothesis is that some, not all, but some or a significant fraction of those prebiotic precursors would form already in interstellar space, and they were delivered to the surface of Earth during the late heavy bombardment period by the impacts of comets and meteorites on the surface. So once those prebiotic compounds reached these kind of warm soups, prebiotic soups, so they could trigger a very rich chemistry. So something that we also consider is that all these prebiotic compounds can survive the entrance of the atmosphere, and there has been some studies in that sense showing that these prebiotic molecules not only survive the entrance, but they also generate even more complex species, organic species, upon the impact on the surface. So as astrochemists, what we are interested in is in trying to connect then the very simple chemistry that we see during the initial conditions of star formation, or the chemistry that we see directly in the interstellar medium, with the complex chemistry that we see on Earth. And then this link, we believe, is provided by what we call complex organic molecules. And for us, astrochemists, a complex organic molecule is defined as a carbon-based compound with at least 6 atoms. Of course, this definition is, for a chemist, this is not a complex compound, for sure, but as you can imagine, so the rotational spectra of these molecules are really complicated, and they get even more complex as we increase the number of atoms in the molecular structure. So for us, these kind of molecules that we consider are prebiotics, because these are the ones that have been proposed as precursors in theories of the origin of life, really present very complex rotational millimeter spectra. So the outline of my talk, I will start showing you our recent results on the detection, on the discovery of prebiotic species in the interstellar medium. And then I will move on to this second area of research that we are doing in our group, which is to try to investigate how that chemical complexity is transferred or is applicable to the initial conditions of a solar system formation. And then I will finalize with showing you, you've probably already seen it in some of Jacobo's work, the work that we've been doing, trying to understand the emergence of the chemical complexity in the interstellar medium by using complex network theory. Okay, so for those who are not familiar with this, with what a complex organic molecule is, as I told you, we consider those molecules with at least 6 atoms in their structure. And you probably wonder, how can these complex organics form under interstellar conditions? So what we believe that the main formation mechanisms occur on the surface of interstellar dust particles in the interstellar medium. And this is a kind of a sketch in which we see that these interstellar dust particles have a core which is formed on silicates and graphites, and then they are covered in these ice whose main content is water, but they also see these traces of smaller molecules that are actually the ones that react on the surface, yielding more complex organics. So here I just list list several mechanisms that we believe are responsible for the formation of these comps, and they involve either the diffusion of hydrogen on the surface, hydrogen atoms on the surface, or diffusion of radicals, so smaller radicals that they encounter, react and form complex organics, or even the non-diffusive. So you form the radicals in the same place on the surface and they react automatically. So that's how we think that they can form in the interstellar medium. In addition, in the past few years, and in order to try to understand the formation of these complex organics, especially under the coldest conditions, in the interstellar medium, it has also been proposed that some of these complex organics can form also in the gas phase. And this is just one example published by Dimitrios Skouteris in 2018, just demonstrating that some of these complex organics can form also in the gas phase. But regardless their formation process, or regardless whether it is in the gas phase or it is on the surface of dust grains that act as catalysts, what it is clear from the past 10, 15 years is that complex organics really permeate the universe. So they are found in all different types of environments, and they are found even in the harshest environments. So this tells you that chemical complexity is a common property of the universe. So here I listed the kind of environments in which we have found complex organic molecules. So the first type of objects in which we detected these complex organics are star-forming regions, or were star-forming regions, such as the dust cocoons and very dense cocoons around protostars, which are very dense, and they are also very chemically rich. And those are called hot cores, which are the dust cocoons around massive protostars, and the hot corinos, which is the scaled-down version of massive protostars. So there's dust cocoons around low-mass protostars. But we can also find these clumsy molecular outflows, protoplanetary disks, photon-dominated regions. So these are regions which experience the intense illumination by UV photons. And even in those environments, we also see complex organics, which is something puzzling, because we will think that these complex organics are efficiently destroyed, even under the illumination of UV photons. We have also found these complex organics in what we call cold cloud pores and starless and prestellar pores. And I will focus on that in the second part of my talk, because what we now know is that these prestellar pores are the initial conditions of solar system formation. And also, they have been found in the Galactic Center, in these giant molecular clouds across the Galactic Center, which are actually going to be the focus of the first part of my talk. So as I said before, the objects that were targeted for the search of these complex organics were these star-forming regions, hot cores and hot corinos. And for this, there has been a lot of work focusing on this type of objects that have delivered a lot of new detections of these complex organic molecules, and in particular of molecules of prebiotic interest. Here I list in particular these two surveys that have been, spectral surveys that have been carried out with the ALMA telescope, focusing on this hot corino. This is a low mass protostar, area 16-93, and this is the PILS survey led by Jens Jorgensen, and also the EMOCA and RIMOCA surveys carried out towards the Sagittarius B2 star-forming region in the Galactic Center, which is a high-mass star-forming region. And as you can see, there is a wide list, a large list of molecules that they have reported in the past now 10 years. The problem when we use this type of objects is that their spectra are really crowded and are really populated by hundreds of molecular lines. So this means that even with ALMA, we are reaching the level of line confusion. What is line confusion? Line confusion is when you look at the spectra, you don't really see any part that is clean of molecular lines. So even with ALMA, even with the highest angular resolution, even with the highest spectral resolution, we are reaching the point in which we cannot really distinguish many other moleculars or any new molecular species. So because of this limitation, other groups have then shifted towards a different type of objects, which are these cold cloud cores, starless prestellar cores. And in this regard, the groups of Pepe Fernicharo and Brett McGuire, they have been doing this amazing work in the discovery of these large molecules, aromatic molecules that are believed to be precursors of polycyclic aromatic hydrocarbons, performing these two large spectral surveys, the Quixote survey using the Yebes 40-meter telescope, and the Gotham survey using the Green Bank telescope. And as you can see, these are some examples of the type of large molecules that they have been detecting in the past few years. They have been extremely successful. So what is our approach? Our approach is something that I would say is in between. What we have been doing in the past few years is that we have been focusing on these giant molecular clouds in the galactic center. So why the Galactic Center? Well, the Galactic Center, it was recognized in the early 2000s, and this is the work of Jesus Martin Pintado, who is in this institute. He's not here today, but he's connected online, I hope. He told me he would connect, so I hope he is connected. And he performed these surveys, these large-scale maps across the Galactic Center, or these single-point observations across the Galactic Center. And what they realized together with Miguel Requena Torres is that wherever you look at across the Galactic Center, they found these complex organic molecules, and they all seem to show a similar amount or similar abundance across the whole Galactic Center. So in particular, they found this molecular cloud, which looks like a telephone number, G0693 minus 0.027, which is located in this point. So it's very close for the astrophysicists. It's very close to the Sagittarius B2 high mass star forming region. So it's part of the same molecular cloud complex. And the peculiarity of this cloud is that it doesn't show any sign of star formation. So there's no star formation at all. So we cannot say it is associated with a hot core, hot corino. There's nothing in there, okay? So the peculiarity of this is that the properties of the cloud are such, allow the shift of the spectra of the rotational lines of these complex organic molecules to shift towards lower frequencies. And what happens in that case? What happens is that if the spectrum shifts towards lower frequencies, this part of the spectrum is much cleaner from smaller species, which is the problem that we faced when using ALMA at much higher frequencies. So if we get rid of the contamination from the smaller species, we then suffer less from line blending and line confusion. So that's really the advantage. Okay. And this is an example of the spectral surveys that we've been carrying out in the past few years with the IRAM 30-meter, the Yebes 40-meter telescopes, and also we have data with APEX. That Victor is the PI, and as you can see there, we have detected more than 170 species. I believe now there are probably more. I think probably close to 200 clearly identified species, and as you can see, more than 50% of them are complex organic molecules. So this tells you that this molecular cloud in the Galactic Center is one of the most important reservoirs of complex organics in the galaxy. The peculiarity of this cloud is that, you know, in contrast to what Pepe Cernicharo and Brett McGuire are doing, they are targeting this cloud, TMC, the Taurus molecular cloud, this position of the cyanopolyene peak, which is very rich in carbon chemistry. What we find with this cloud is that the chemistry is very rich not only in carbon-bearing species, but it's also very rich in oxygen-bearing species, in nitrogen, and in sulfur-bearing species. So whatever molecule you want to look at, this is probably one of the best places to search for any new molecule that you want to identify in the interstellar medium. And indeed, so if we compare the chemistry of this cloud with a typical star-forming region, which is Sagittarius B2, so this is the work that we've been doing together with Claudio Codella and Arnaud Beloche, and this will be hopefully published this year because we've been waiting like more than a year and a half in this handbook of astrochemistry. So what we've been doing is comparing the chemistry of these two sources, and we indeed find a very peculiar chemistry for this cloud in which it is very rich in amines, for instance, amines, imines, and as you can see here, they are extremely abundant compared to a typical star-forming region. We also see that it is enhanced in sulfur-bearing species and also in any other species that we say it's unsaturated. So it shows a little or low number of hydrogen atoms. And we believe that this very rich chemistry is driven by the extreme conditions found in the Galactic Center, which are dominated by the presence of low velocity shocks and enhanced rates of cosmic rays. Okay, So now we have our target of a study. So we know the object that we really want to look at or we want to use as our lab. And then what we need to now try to find is the species or the prebiotic species that we want to look for. So, and this is, Carlos is not here, but this is something that we started with Carlos Briones, who pointed out this beautiful work by the people of from the group of Sutherland, Pauner in 2009 and Patel in 2015, in which they proposed all these chemical schemes that, as you can see here, they start from very simple molecules, and they are able to build up not only precursors of RNA with these pyrimidine ribonucleotides, but also precursors of sugars and proto-lipids, and also precursors or even amino acids. So what we did was we inspected this diagram closely, and as you can see here, all the molecules that are or that have these blue circles were the molecules that were routinely detected in up to 2019, and then in red are the ones that were not identified in the interstellar medium up to that date when we started looking for these species. So in 2019, we reported the detection of this one, of glycolonatril, which is an intermediate species in the formation of sugars with 3 and 4 carbon atoms. And then encouraged by this, then we decided to start or to continue looking for these molecules that were present in this chemical scheme. And in particular, we focused on urea, 2-aminoxazole, this is glyceraldehyde, and dihydroxyacetone. And this time we used spectral surveys that we had towards our cloud with a relatively poor sensitivity. So the spectral surveys that we have now are much more sensitive. And in these first searches, we reported these upper limits for these sugar like species, glyceraldehyde and dihydroxyacetone, which were consistent with previous searches. We reported the detection of urea, and it was just really a shame because by just a couple of months, we were late with respect to the detection reported by Arnaud Beloche in 2019. But in any case, this still is the second source in which urea, which is an important prebiotic precursor, has been reported in the interstellar medium. Then, unfortunately, we really wanted to detect the 2-aminoxazole, but then this molecule was not detected at this time. And then this difference between the behavior of 2-aminoxazole and urea attracted a lot of interest, especially of the material physicists and on people who are interested in understanding the chemistry of these molecules in space. And by talking to Belén Maté and Víctor Herrero at the Instituto de Estructura de la Materia, they performed these experiments in which they used ICES, or interstellar ice analogs, formed by just using pure urea or pure 2-aminoxazole or even mixtures with water. And what they did was to irradiate these interstellar ice analogs with UV radiation and also with highly energetic electrons simulating the effects of cosmic rays. And what they found is that these two molecules actually they get destroyed in a different manner. While urea is much more resilient to irradiation, 2-aminoxazole gets destroyed very easily. So this tells you, even if 2-aminoxazole is formed in interstellar medium under interstellar conditions, it would get destroyed very easily. So that will tell you the kind of prebiotic species that are more likely to reach the surface of Earth during the late heavy bombardment period. Then at the same time, or at that time, so there was also this work by Becker and collaborators in 2019 from the group of Thomas Karel in Munich, where they presented this new chemical scheme in which by starting from very, very simple molecules, again, thank you very much, from very simple molecules, they could form concurrently not only pyrimidine ribonucleotides, but also purine ribonucleotides. So if we inspect this diagram again, so we see the same suspects. We see glycolaldehyde here, we see formaldehyde, we see urea, interestingly, and also hydroxylamine, no? And this was the motivation for start looking for this molecule. And this is the work of Victor Rivilla, who is sitting there, who started searching for hydroxylamine, and then this is the reported the detection of this molecule that he reported in this paper in 2020. This source is indeed very rich in amines, as I said, in molecules with this amine group, which is this NH2. And in 2021, Xiao Shanzeng, who is my former PhD student from London, she reported the detection of vinylamine and the tentative detection of ethylamine. I think ethylamine now is robustly detected in the new surveys. So as you can see, this source is also very rich in this type of molecules, and these molecules are believed to be precursors of amino acids. This is also a very nice work of Victor, who published in 2021 with the discovery of the simplest phospholipid head group, ethanolamine, as you can see here. So there are two different types of phospholipids, and in this is one of them. And ethanolamine is the head group, so is that molecule that is indicated here in this diagram. So in this work, Victor could establish the amount of ethanolamine present in interstellar medium, whose abundance is of the order of 10 to the minus 10. We could estimate that the ratio between ethanolamine and water was actually consistent, or was very similar with what has been measured in meteorites. So by using this abundance ratio, then we could estimate that about 10 to the 15 liters of ethanolamine, which is equivalent to the capacity of the Lake Victoria, could have arrived to Earth. So what we proposed in this paper is that in a primitive Earth, what one should expect to find are these protomembranes formed of fatty acids and fatty alcohols. So what we proposed is that the arrival of ethanolamine could have contributed to the insertion of this ethanolamine molecule into the structure of these simple protomembranes, yielding the formation of phospholipids and membranes composed of phospholipids. There has been a study that has triggered the revision of some of the theories for the formation of protomembranes. So it has been really an inspiration for people working on prebiotic chemistry. And because we had the hedge of the phospholipid, then we decided to look at was the precursors of fatty alcohols and fatty acids. And this is something that we reported in 2022, which was the detection of N-propanol in the different conformers. So as you can see, the larger the molecule, the different shapes it can take, and the different conformers, and all these conformers are different species that you need to identify on their own, so independently. So you can see that the analysis of the data set gets even more and more complicated. Something that it is very interesting and that we found in this paper, and that we have found also for other chemical families, for sulfur and even for nitrogen, is that we see a common trend for these molecules to decrease their abundance by a factor of 10 when we insert a new carbon atom in their structure. So this is something that can help us to try to see whether even larger molecules could be detectable, no? So we have enough limits, sensitivity limits, to detect the largest or the next step in the chain of complexity. And this is basically the summary slide, where in the past few years, we have reported the detection of 23 new interstellar molecules. And here is just an example, but here we have precursors of ribonucleotides. We have also precursors of protomembranes, even molecules that are believed to be, or that are believed to be catalysts in the formation of proto-proteins, and precursors of amino acids. So I would also like to mention that we have not only detected prebiotic molecules, but also the molecules that are of interest for astrochemists. And here I just also would like to mention the work of Miguel Sanz Novo, who was also in the previous slide, and also Sara Masalhi and Marta Rey Montejo. In particular, now we have this paper that we have just submitted, is under review with the detection of this sulfide, sodium sulfide and magnesium sulfide, which may be, we need now to try to understand whether these are important reservoirs of sulfur in interstellar dust grains. And of course, because we are detecting new molecules, they trigger a lot of interest in the astrochemist community, and there's a lot of work from groups working on quantum chemical calculations, trying to understand how these molecules form and how they behave under interstellar conditions. And I would like to mention all these works that are related to the molecules that we have reported in the past few years. Okay. So this is what happens in the Galactic Center, but should we expect to find similar chemistry, but in regions that are closer to the initial conditions of our solar system? So what we have been doing at the same time is we have been trying to establish whether we see the same level of chemical complexity in what we call prestellar cores, which are now accepted as the initial conditions of solar system formation. What is a prestellar core? Because you are probably not familiar with what a prestellar core is. So a prestellar core, as I include in there, so these are these dense and cold condensations. And we know that they are prestellar, so they are going to form a solar type system because there's evidence that they are gravitationally collapsing. So they are collapsing, they are contracting, and therefore they are going to form a solar system, a planetary system. The interesting thing is that because these condensations are very cold and are very dense, initially it was expected that these complex organic molecules would not form under these conditions because they were really extreme for these complex organics to form. Surprisingly, in 2012, and this is the work by Aurora Bachmann, yeah. She reported the detection of these complex organics in one of these prestellar cores. So then the community really started searching for these complex organics in many different prestellar cores, in many of these cold cores, and we have found that they are really ubiquitous in these type of objects. So why is it important to find these complex organics during the initial conditions? It is important because it has been shown that probably a significant fraction of the chemical composition that we see in comets come from those initial stages in the formation of a solar system. So that's why we want to understand the level of chemical complexity in these cores and whether that chemical complexity is really related to the chemical composition that we see in comets. So how do we study the level of chemical complexity in these prestellar cores? You need to think that these cores, because they are dense and they are very cold, the emission from these complex organics is really weak. Therefore, it is really challenging to observe and to detect them. So if you really want to know about how these complex organics form, where they are located, and so on, you really need to do it, at least with the current instrumentation, by performing just very deep integrations toward certain locations in the core. And this is what we did in 2016, choosing this prototypical prestellar core L1544. So what we did is in these observations was to target these two positions in the core that I show here. So this is the emission of methanol, which is the simplest complex organic molecule that we know of. And as you can see, we targeted this position towards the center of the core, and then this other location in which methanol was very rich. So what we tried to do was to perform these deep observations and then see the differences in the abundances towards these two positions. What we found is that there was a clear enhancement of these complex organics molecules at this position in the outer shell of the core. And this outer shell corresponds to a distance which is about 4,000 AU, which is equivalent to the distance of the Oort cloud in our solar system. So what this means is that this region, this outer shell in this prestellar core, and what we have found also is that it is common in other prestellar cores and in other stellar cores, is that the chemical complexity is enhanced in this region in all these cores, in these Oort cloud-like regions in these young planetary systems. So what we believe is that this chemical complexity, and in particular the chemical complexity of this oxygen-bearing COMs, as we call them. So it's enhanced or is produced, is driven by the catastrophic depletion of carbon monoxide, of CO. What happens in this region is that carbon monoxide is depleted. It sticks very efficiently to the surface of dust grains, and that triggers a very active chemistry on the surface, producing many complex organics that are then released back to the gas phase. So this location, or this location that we observed with our observations, is equivalent to what we call the CO snow line in interstellar cores. And we believe it is probably one of the richest repositories of complex organics in this type of objects. As I said before, so this behavior is similar in other established cores, and this is the work of Andrés Mejías, who is sitting there, who is doing the PhD now. And as you can see, there's also an enhancement of these complex organics in these outer shells of established and interstellar cores. There are differences depending on the chemical families between the oxygen and the nitrogen beam, but it seems that this region is very rich in these complex organics. So what we think is that the chemical complexity increases with time as core collapses in the way to form a solar system. This is, of course, what happens in the gas phase, but what happens in the ice, right? Because as I said before at the beginning of my talk, what I told you is that we believe that the main formation mechanisms for these complex organics occur on dust, occur on interstellar dust particles. So what we really want to know is whether we see those complex organic molecules also in the ice, in these dust particles. And this is what we've been doing. This is the work of Miwa Goto in 2021, in which we inspected by using infrared spectra, absorption spectra, towards this background star number 3. And this is the same core, L1544. So we pointed our telescopes, this is the IRPF telescope, towards this star 3, 1, and 5. And this is the absorption spectrum obtained towards star 3. This is the typical feature for water. This is the water ice. And then we also found a very small feature here, a 3.53 micron, which we identified as methanol. As you can see there, the fraction of methanol that can be found in this also outer shell, so it's all coincident with this outer shell, is about 11%. So we have in this interstellar core a fraction of methanol of 11% present in the ice. But of course, the goal of this is not only to observe methanol, but to even go to higher or to more complex species. And this is the goal of this early release science program, ICE, in which the goal was to try to understand the chemical evolution of ices along the process of the formation of a solar type system. In this first work that was published by Melissa McClure in 2023, we focused on these two positions of the chameleon-1 molecular cloud. So this is the chameleon-1 molecular cloud in here. And these are the two background stars that we targeted within the Ice Age program. This is called NIR38 and J110621. Which show very high extinctions. So these were actually the first observations performed, ice observations performed towards the stars with the largest extinctions. So this was really a major step forward in our understanding of the chemical composition of the ices in molecular clouds. So these are the spectra that we published in 2023 in Melissa's paper. And as you can see here, so we detected many different species. So we have the water, this is the water band. We have the typical CO2, CO, but there are also some features of methanol, methane. We have even a tentative detection of OCS, SO, and these are the typical abundances. So what we established in this paper is that methanol ice can form very early on in the evolution of star formation, in the process of formation of a solar system. In a follow-up paper done by Emmanuel Dartois, we also found that that grain growth also occurs at this very early stage. And it is a very nice paper. So if you want to have a look at, so you will see how by including grain growth, it really matches very nicely the shape of the water absorption line and all the different features observed in the spectrum. And what we are currently doing now, so because we have the observations, what we want to do is to try to understand how all these molecules form in the ice. And this is a huge effort from the chemical modeling community within the Ice Age collaboration. And I would like to thank all the modelers that have joined. Angel is here, so Angel Dayal, so she has done some of the modeling for this work. So what we've been doing is we have been gathering all the different groups with state-of-the-art astrochemical codes. And we've been running all these different codes to try to understand whether we can reproduce the abundances, the ice abundances that we detect with Ice Age, with the James Webb. And as you can see, they're doing a relatively good job. There are some differences between the codes, but what we clearly know now is that methanol, in particular, which is the simplest complex organic, forms via the hydrogenation of carbon monoxide, which was something that had been proposed, but now seems to be many years back. There was some controversy in the past few years because there was some theories proposing that there may be other mechanisms in water-rich environments, but now it seems that to form methanol, thanks to this modeling, methanol is formed via hydrogenation of carbon monoxide. Okay, and then what we are also trying to do in this sense, and what we would like to do in the future, is to try to identify, of course, these complex organic molecules in the ices. And for this is the work also of Andres, who is developing this new analysis tool to identify these absorption features for complex organics by using artificial intelligence, and in particular these neural network techniques. So by using what Andres is doing, so he's using these neural networks, he's training the network by using this infrared spectral database, in particular this one in the LIDAR catalog. We now have other input from other labs, no? Because these are all spectra that are taken in the lab. So then Andres trains the network with these ice spectra, and then we see that the validation is very nice, as you can see here, because it is the true fraction. This gives you the true fraction of water, CO, CO2, methanol, ammonia, and methane that we know because we put that fraction in the lab. That's what we measure from the spectra. And this is what the neural network gives you. No? So we input the ice spectrum, our ice spectrum from the James Webb, and then we apply the neural network, and then the neural network will tell you the fraction of each molecule is present in the ice. Okay, so that's the philosophy behind it. So he has applied this neural network to one of these stars, near 38, and the other one, I think, 2. No, you have also the results for the other source. And as you can see, so it gives very nice results. And in here, what he compares is the output of AIs, this automatic ice composition estimator, and also the estimates by using other methods that are available in the community. So as you can see, it's doing a great job. The real advantage of this neural network is that it is very fast. No, so it runs even in the order of milliseconds. No. 0.1 second. Yeah, 0.1 second. So it is super fast. So because the James Webb is providing all this information from hundreds of sources, so that means that we can do this analysis for hundreds of sources in just a very small amount of time. So it's really an advantage compared to previous methods that are available in the community. Okay, and in the past, I think in the past 2 minutes, what I would like to mention is the work that that Jacobo has been doing, and the work that we've been doing in collaboration. And you have probably seen this because he gave a talk on this this year as well, which is NetWorld, which is this new framework that he has developed based on complex network theory to create this artificial chemistry of networks. So in this case, what he's doing is, so what we did in this particular case, so he had this beautiful framework of networld, and then he came one day and then he said, do you think we can apply this to your case, no, to interstellar chemistry? I said, okay, well, let's have a look, you know? And then we just found out that if we compare the results of networld, and if you compare it with the abundances that we see of interstellar molecules, it really gives a very nice match. So networld, the way it works is that, as Jacobo explained early on in this year, so networld, so we have a network we have a node, so a collection of nodes. These nodes can interact between themselves, so they can either join together. There's also a probability for this destruction of the bonds, and they interact, and then they can create bigger and bigger networks. So in the end, what you get is a network of networks. The interesting thing is that networld doesn't include any chemistry, so it doesn't have any chemistry theory at all. So it was very interesting to see whether we could reproduce the observables of what we see in the interstellar medium. So what we found is that if we go beyond one critical value for this parameter, this beta parameter in the model, and this beta parameter basically engulfs everything that is related to the environment, to the physical conditions of the environment. So if we go beyond this critical point, then chemical complexity explodes, really increases. And when we compare the results just one by one from networld and with the behavior of the abundances, of the molecular abundances that we see in interstellar medium, and this is what it is shown here. So this is the output of networld, you see, for the different beta parameters, the different values of the beta parameter. And these are real data. So these are the ranking of the abundances of molecular species for molecular clouds with different physical properties. So we go from diffuse clouds, which is the black, from translucent cloud, which is the green, and then dense clouds, F134 and TMC1, okay? And as you can see, the chemical complexity really explodes for dense clouds, which are consistent with the fact that the beta, that probably their beta, associated beta, is beyond the critical value for that parameter. So networld, even though it doesn't include any chemistry theory, really mimics the behavior of the chemical complexity that we see in interstellar medium. And this is basically everything, all the projects of the ERC Consolidator Grant, in which the three main goals are the ones that I have told you today. So we would like to understand what prebiotic molecules can form in the interstellar medium, which one of those prebiotic molecules are also transferred to the parental molecular cloud, and we would like to try to understand the emergence of chemical complexity in the interstellar medium. And this is everything that I wanted to tell you about. I leave you with my conclusions, and if you have any questions, I'll be happy to answer them. Thank you.
Thank you so much, Izaskun. It's very nice talk and amazing work. And we have time here for a couple of questions.
Yes, can I put a question?
Yeah.
It's Michel Guélin from IRAM, yes. It's a very nice talk, and I thank you for that. I have still one question. I mean, you start by the idea that after all, these molecules were formed with the help of carbon and grains, and they came to the Earth from comets or meteorites. But isn't it more simple to use the same conditions that you find at some epoch on the Earth to form directly this molecule on the Earth, because the density is so much higher? And you have water, relatively soon water, etc. So I mean, I agree that if you go very far, we have looked very far at galaxies at high redshift, and you start to find the same molecules, of course, not as complex, but still. It's clear that the chemistry is more or less the same everywhere. But do you need really to get life coming, or this molecule coming from outer space?
Thank you very much for the question. Yes, so that's what I said at the beginning. No, so our work hypothesis is not. So we are not saying that all prebiotic molecules, all the prebiotic compounds have to be formed in outer space in the interstellar medium, and then we transfer to the Earth. So what I said is that a significant fraction could have contributed to these first steps in the origin of life. And one of the examples that I really think is very clear in this, especially in these theories, these prebiotic chemical schemes, they typically invoke the presence of sugars or of sugar precursors, no? Like glyceraldehyde. Glycolaldehyde is, of course, always present in these chemical schemes. And the problem that they are facing when you ask them is like, okay, so you really need glyceraldehyde, but how do you form it in the first place? And this is a challenge for them. So sugars cannot be synthesized prebiotically. So what I'm saying here is that there may be some of these key ingredients, some of these key compounds that were not easy to form under prebiotic conditions on Earth, but some external source that could have come from the interstellar medium could have contributed to trigger this very special chemistry. Does that answer your question?
Thanks, Izaskun, for this fascinating talk. I have a couple of questions. The first question is very related to what this person just asked. And it is, do you think that life would have appeared on Earth without all this chemistry? That would be the first one, which is just a guess. And the second one has nothing to do with that. It has to do with a nice picture where you showed that there is a relationship between the abundances of different molecules and the complexity that it goes decreases exponentially, which is the error there. And can we see this?
Yeah. Use the propanol. This one. The arrow bars are in there. So,
sorry.
But they are very small.
And if
the triangles, so the triangles is the predictions. Sorry, I didn't explain. So the actual measurements are the squares, and then the triangles are the predictions from a model, from an astrochemical model. So it was just to show that there was a good match between the observations and the astrochemical modeling.
Okay.
And then regarding the first question, you're asking me something like so what you're saying is that whether you could form life without the chemistry in this chemistry in the interstellar medium.
You think that life would have found its way somehow?
I mean, what we are proposing is that there may be some of these molecules that may be very difficult to form under prebiotic conditions, but that could have been available from the externally, no, from the impact of meteorites and comets. Phenolamin, for example, is a very nice case as well, no, because so if you could have something available and in large quantities, no, some of these molecules available, so it would have been easy to be inserted. And this is the work of Szostak, I think, no, Victor? Szostak, no, that they show that they start with these very simple proto-membranes of fatty acids. And then when they start inserting all these molecules, so they start forming these phospholipids. So it could have assisted.
All right.
Well, maybe just to point out that the idea on the beginning that life was coming from outside was a question of time. And the idea was that, of course, you will have, if at that time we did not know what was the age of the universe, right? And the idea was that it could be very, very long, and some people were not believing in the idea of a Big Bang, right? And they were thinking that the universe was in a steady state, and therefore you have an infinite time to fabricate by chance these molecules in space, right? Hoyle was one of the proposers of that theory, right? And of course, now we know that this is not the case. And you need some time to form molecules. But then the density is, of course, something extraordinarily important. And when you compare the density in these clouds at the surface of the grains, which were relatively rare, with what you find on the Earth, of course, you are much stronger on the Earth. Okay,
Yeah.
it's just a comment.
Yeah, absolutely. We are just providing some new ingredients for people, experts in prebiotic chemistry, to start thinking that those compounds may have been, those ingredients may have been available, and providing new routes for the formation of these first biochemical compounds.
Okay, that's a very nice talk. Thank you.
Thank you. You're Michel Guelan, right? Are you
Yes.
Michel Guelan?
Yes, yes.
Yes. Nice talking to you via Zoom.
Okay, show my face.
Hi, thank you. So this is completely out of my field, but I was amazed by your presentation. Thank you so much. And congratulations for the ERC. So my question is, if I understand correctly, the idea is that there is no one single one-pot experiment that simulates the terrestrial complexity and emergence of life. And since the Earth is not isolated from space, why not considering what came from external sources and in what amounts? And that is where you're contributing. So the other question is then, the question is, one of the main problems on Earth is how chirality selection started on Earth. Would there be any source for chiral selection in space?
Yeah, this is something that we discussed a lot with David Hochberg. So this is something that we actually started a project together with Juan García de la Concepción, who was a postdoc here. And then the idea was to try to investigate whether under interstellar conditions you could induce an enantiomeric excess.
Exactly.
No? So one of the possibilities is by irradiation of a circularly polarized light. So that's one possible mechanism. We are now also trying, and this is also part of the project, so I didn't put it, but this is also part of the project. And then we are also trying to investigate now whether by using whether by using some graphites, no? So in the stardust grains, as I said, so the core could be either silicates or graphites, no? So whether if we use graphites, like, such as, for example, graphene, no? It has been proven recently that if you put methanol on graphene, it shows these kind of structures, or it produces new chemical structures which are chiral. Okay. No? So one possibility that one would like to explore is whether, of course, in interstellar space, you need to consider the graphene, the graphite, and then you need to put the ice with water on top. So what we want to do is whether that kind of structure of the dust and of the ice could induce that chirality.
Okay.
But it is very complicated. So it's something that Juan has been thinking about, over the years, and it is very difficult. What it is true is that there has been some measurements. I think, I don't remember now the first author, Guillermo Muñoz Caro knows, but there has been some enantiomeric excess found in meteorites. So even if you have a very small amount, like of even less than 1%, once in aqueous solution, then that induces the homochirality.
And the other thing I really like is new work, which is under development now, about neural network uses for rapid identification of spectral bands. And I happen to notice that everything was perfectly matching with the exception of the temperature.
Right, yes.
So how bad is that? Is that because it's like everything is super cool and then it's still cold, but not that cold. So
not that cold.
does it create a big problem? Does it shift the bands?
Yeah, so that's the thing, that with the temperature, the shape of your bands change a lot. So, and you also need to take into account that we are working with a very limited amount of a spectrum. So these neural networks typically work, or they are trained with thousands of the spectra. Here we are working with 500, which are the 500 spectra that we have from the lab. Now Andres, so he has managed to do some synthetic spectra from just pure mixtures, which is something, it's a proxy. So it's actually not exactly the same as what you would get in the lab. So we are now trying to talk to people who in the lab to see whether we can enlarge the database, because this is really crucial for the neural network to work very, very well. I mean, with what we have so far, it really works very, very well. So it's very promising.
Fantastic. Thank you.
So we have time for one last question, if there is any here. So Jacobo.
Great. Then I'll ask another thing. Regarding that, there are now this new James Webb Telescope. We have ALMA and all these different structures. In your opinion, how far are you from being able to detect the whole chemistry in the interstellar space? The 350 molecules that you have already found, which is, in your opinion, which percentage of the real thing does that represent?
Okay, so far, so we have detected more than, in general, the community, more than 300, no? I think it's close now to 320, no? And actually there has been an explosion in the past 2-3 years. And especially thanks to the GBT and Yebes, mostly Yebes. So this has been a huge, a huge step, no, in our understanding of the chemical complexity. Here, the bottleneck, well, so of course we would like to have new instrumentation in the future, especially at lower frequency with very high sensitivity. But here the bottleneck is to try to get the spectroscopy. So you really need to convince the different groups, no, experts on microwave and millimeter spectroscopy to obtain the spectroscopy so that we can look for those molecules in our spectral surveys. So that's really the bottleneck. And for some of these molecules, they are very difficult to be synthesized. So to synthesize them in the lab. So it is not as straightforward. No? I mean, the techniques are really amazing. So now we are getting a spectra, the millimeter spectroscopy for sugars, no? For sugars with 4 carbon atoms, 5. No, this is the work that Emilio Cocinero is doing in the Basque Country.
But then you would say that what you've seen so far is a good description of what there is, or you're just looking at a very, very small part of the whole chemistry that could be there? In which part are you? I mean, the community in general.
Can you repeat the question?
So these 320 molecules are, which percentage, if you want, of the real chemistry are they describing? So you're just looking at a very, very small part of the reality, or you think that more or less this describes more or less well?
I mean, we are going, because we are going deeper in our spectral surveys, we are targeting molecular species that are less and less abundant. No? So they are not going to be the most abundant species although, I mean, Miguel, he's not here today. There he is. Miguel, for instance, so his work on carbonic acid was really, really nice because he reported the detection of one of the conformers, no, of carbonic acid, the trans-cis carbonic acid, which is the one that has a good dipole moment so that it can be detected. However, he estimated that the main one, or the most abundant one, should be the cis, right? And by several orders of magnitude. So there may be some cases in which those molecules in those conformer states may be abundant, but we cannot reach them because they don't have a strong enough dipole moment. So we are limited also by that. No?
Right. Thanks a lot.
Victor,
congratulations for the grant.
Yeah, to answer your question, from my point of view, I think that the percentage of molecules that are in the interstellar medium that we have detected so far is low. I think is my personal view, is quite low because 1/3 of the 320 molecules that have been detected, almost 1/3 has been detected in the last 5 years. So the increase is exponential, and this has been doing thanks to the very sensitive observations that we have been done. So the deep you integrate, you get access to weaker emission from less abundant molecules. So even the question is how complex could be. This is very difficult to predict, but I think that is much more complex than the level in which we are so far.
So thank you again, Izaskun, and thank you all attendants here and online, of course.